Welcome everyone to the third edition of Sparks. It's the first one that takes place in this new auditorium at the Science Gateway. Emmanuel Macron was in the building 2 hours ago, now it's you. So it's a good day for CERN and for the Science Gateway. I'm Bruno Giussani, I will guide you through the evening tonight. Sparks is a forum that CERN has created to explore new cutting-edge developing technologies, looking at their links to science, of course, and looking at their impacts on society. And also looking at their links to art. The animation we just saw has been created by an artist, Elul Duranagach Alici from Ush Studio, a long-time collaborator of Spark. She used 73,000 data points from interferometers, the machines that detect gravitational waves, such as the Hubble telescope or LIGO. You may have heard of them. In every edition, the editions are normally annual, Sparks focuses on one particular technology, looks at their core elements, looks at the different potential applications, considerations that are of ethical or practical character. In the first edition, we looked at future intelligence, machine learning, artificial intelligence. Since then, 3 years ago, it has exploded into the public domain, as you know. Last year, we explored future technologies for health, and we also accompanied the conference with a 6-episode podcast on that topic. And this year, we're going to look at future quantum technologies and science, because we are at CERN. So in the next 105 minutes, something like that, we want to look at different aspects of quantum, 2 talks and discussion. What is quantum technology? What kind of applications we can expect in fields like computing, healthcare, cryptography, material science, energy, telecommunications, and beyond that. And of course, also, we will talk about quantum at CERN. What happens here, what thinking around quantum happens here, and what practical applications. Before we start, 2 quick items of housekeeping. First of all, in case of emergency, the 2 emergency exits are just behind you on both sides, and we can exit both sides. And second, don't forget to turn on your phone again at the end of the event. But for now, silent, screens off, phones away. We don't want a screen to pop up in the middle of the darkness of the room. It disrupts the attention of people around you. It also distracts you from paying attention to the speakers, and I hope that you will actually give your full attention to the speakers. So, quantum technology and quantum science. What many non-specialists know about quantum is that at very small scale, the scale of electrons, protons, ions, things behave weirdly, behave counterintuitively. For example, particles can be entangled, they can be connected even over a distance, or they can be in 2 different states or multiple states at the same time. These are not easy things to understand, and the fact that we know those things doesn't mean we understand them. It's a field full of promise. It's also a field that can be really head-spinning in many ways. So tonight we're going to try to give a glimpse into some of this, and hopefully we are all going to leave this room at the end with a better understanding of all this. One thing that's sure is that for 100 years now, because quantum has been developing over almost a century, the quantum science and technology have become central to many fields, and certainly looking forward, they're going to be an enabling set of technologies for many different areas. The first step in exploring them is to look at the evolution of quantum information theory, where CERN played a big role at some point and still does today. And so the opening speaker works at CERN, researches at CERN. She researches scientific computing, machine learning, quantum computing, and of course their applications to high-energy physics. She's a member of the CERN Quantum Computing Technology Initiative. It is a pleasure to welcome on stage as the opening speaker, Sofia Vallecorsa.
Thank you. I will talk to you about the promises of quantum revolution. What do I mean by that? I will explain to you what it means, how it came to be. In fact, we talked today about 3 quantum revolutions, and I will try to let you get out of here, those of you that are not physicists, with an idea what quantum mechanics is and how we can use it actually to build technology that we can use every day. So let's start right away with three simple concepts. I am sure you have heard about them many, many times, and I'm sure you've been wondering what exactly they are, how we explain them, how they came to be. So I will go through those three concepts, and then I will explain to you a little bit that this was actually a struggle to get to really understand how those three concepts can explain the reality, the fundamental properties of matter and interactions and everything that is around us. So let's start with the quantum superposition. So the idea that a quantum state, if you can think of fundamental particles, for example, exists only in a superpositional state. The classical example that you can use, for example, if you look at the coin that's pictured in the slides just behind me. So the difference is that if you have it in your hand, then you can clearly, very easily see if you're looking at one face or the other. But if you spin it over a surface, over a table, then the two faces are really merging into each other, overlapping. You can't tell which is which. The only way to actually see them is by stopping it. So you can't say anything until that coin has stopped spinning. This is something that gives you a picture, helps you picturing what actually means when you're thinking about quantum states. And this is a very important property which we can use today, for example, to build quantum computers. It gives us the possibility to store a much larger amount of information that we could on classical devices. Tunneling is another interesting topic. The definition of tunneling is a particle, a fundamental particle, for example, can go through a barrier, an energy barrier, even if it doesn't have enough energy to actually do so, in principle, okay? So this has been observed, this happens all the time. But I'm sure you experienced that also when you go up the mountains. How many times you felt like you did not have the strength to actually go all the way up and then maybe go down the other way? And wouldn't it be great to actually see a tunnel, completely flat path that would allow you to go through the mountain without expending so much energy, okay? This is actually another concept that we can use to build more powerful tools for our computing, more powerful computers, okay? And I will get back to it. Entanglement is the third concept I wanted to talk to you about. It's also something you will hear more about later on through the evening, so I will not spend much time. Let me just tell you that the idea of entanglement is one of the most, from the beginning it was considered one of the most mysterious in some way, the most difficult to reconcile with what physicists knew at the time. It's the idea of two particles that are separated in space and they can still be linked to each other. They can still influence each other in some way. So this is a concept that was introduced very early on in quantum mechanics, and it was really one of the things that physicists at that time, that many physicists at that time could not accept. So they were really trying to find alternative explanation rooted in classical, in what we knew about physics up until then, in order to explain it. So, why do I stress how difficult or how far from the reality we all know those kind of concepts feel? Because indeed, once they were introduced at the beginning of the past century, we started to experience what is today called the first quantum revolution. In fact, people tend to think about three of them, two of them. One happened already in the beginning through the, let's say, past century, another one through the 21st century, and there are also people talking about the third quantum revolution that's already about to happen. Once this technology will allow us to really bring disruptive changes to the way we do science and we use technology today. So let's start at the very beginning. I mentioned three principles of quantum mechanics. Quantum mechanics is one of the most exciting and successful theories in recent history, scientific theories in recent history. It all started at the beginning of the 20th century with names, with physicists that you might have heard of, Max Planck, Einstein, Heisenberg. They all contributed their own little bits and pieces that helped us arrive to what we know today and to actually build technology that you can use daily. Transistors already many, many years ago are possible because of what we learned through quantum mechanics, GPS systems, lasers. Okay, all of those those technologies that are very friendly and familiar, I would say, they are possible because we learn how to interpret reality through quantum mechanics. The idea, for example, of a duality between particles and waves. You can think of a particle as if it were a small packet of waves, and they behave in the same way. Entanglement, as I mentioned before, and this idea of superposition. So that's why we talk about first quantum revolution. The initial ideas of quantum mechanics, the struggle through the scientific community to understand how the new ideas could be reconciled, could be matched to what was already known and what was observed through experiments. And then let's say, all of the technology implications that came from it. So CERN did participate in some way to bringing up this quantum revolution, okay? That we talk about it in the years 2000s, but it's actually started much earlier when John Bell was working at CERN and he proposed a mathematical proof that actually showed that some of the concepts, some of the phenomena that quantum mechanics can explain cannot be explained by any other theory, any other pre-existing classical theory. Okay, so he gave us a proof that we need quantum mechanics to explain some of the behaviors that we see around us today, that explains how fundamental particles work. And that was a very, very important step. At the beginning, his work was a purely mathematical proof. I am an experimental physicist. I want to see things. So in some sense, I could look at that as something that is very detached from reality. But it was a very important tool because through the years, so this happened in the 60s, and through the years, that was the seed of a series of experiments that actually proved in many different contexts that his initial ideas and his explanation and the need for a quantum explanation of reality was actually true. In fact, this led to the Nobel Prize in Physics last year. This is how it started. It was, again, kind of a struggle, a long path, a lot of physicists that contributed their own way, paradoxes that were proposed, and explanations that came many years after in some cases, okay? What do we know today about quantum? Actually, we know that we can use it in many, many different ways. What really changed in what we call the second quantum revolution is the fact that we understood so well how quantum mechanics works that we are now able to build artificial quantum states. We can produce them at a very accurate level, and we can leverage them in our technology. Okay. So we can build sensors to do better detectors, to do better imaging, for example. We can build computers to store more information than we could with classical computers and to perform operations and perform algorithms at a much higher rate, much faster, more efficiently, hopefully. We can simulate processes that otherwise would require entire huge clusters of classical computers to simulate. And we can do that just with a handful of qubits. And then there is the whole discussion about quantum communication. This is something that the general public is very, very interested in. And it's a whole discussion about security, how quickly and securely we can share information across maybe different regions in the world. Okay, so the possibility through entangled states to actually transmit information across long distances. So all of this is something that exists in many, or is being studied in many different fields of science. But what is it that CERN is doing today concerning quantum, okay? John Bell was working here. Somehow we started, or we contributed to the beginning of the quantum revolution. What are we doing today about this? So since 2020, CERN has launched its Quantum Technology Initiative. And the idea of this initiative was really to try and understand in the most, I would say, realistically possible condition. Do you say that in English? I'm not sure. But in conditions that would be as realistic as possible, what is the impact of this kind of technologies? Okay? Because we are physicists, we need to be able to understand exactly to which extent we can use this. What does it mean to use it? How can we maybe use physics to improve it? And so if you look at the four main areas, topics that the QTI covers, you can see that kind of maps map the four main areas I mentioned before of how people are using or are looking into quantum in the world. So we started looking at it from a theory perspective. So can we use quantum computing to simulate physics processes? This seems just, reasonable, because physics, what we do here is actually explained by quantum mechanics natively. Okay, this is the house of quantum mechanics. It should be very fast. We are looking at communication point of view. We are looking at sensing. We are building accurate, good detectors is something that is very, very important for us. So can we leverage quantum mechanism to build better detectors? This is a crucial task that the community at CERN has. Let me just remind you that we are the largest laboratory for particle physics. We have at the moment the largest accelerator. This is in general the largest experimental facility that you can find worldwide. So the LHC, the Large Hadron Collider, is generating collisions in four main detectors, and each one of them, they have different, let's say, objectives. Well, some of them overlap, but they also have, each one of them, their own specialty. Okay, and you can think of all of them though as very big cameras that take very precise, high-resolution pictures of what each collision produces. Okay. LHC is kilometers and kilometers long. We are talking about petabytes and petabytes of data. This is definitely a very big computing challenge. So all of the physics that we know that CERN physicists could do up until now was possible thanks to a huge computing infrastructure. It was the example of the first large-scale distributed infrastructure many, many years ago. It's called the LHC computing grid, and it's a network of computing centers that is spread all across the world. So that was needed, for example, to give you results like the discovery of the Higgs boson in 2012. And as I said before, we already know that WLCG, so the LHC computing grid, as we use it today, will not be enough to face all the challenges that we are ahead of us with the next generation detectors. Okay, so there are many technologies physicists are looking into, and quantum computing is one of them. How do you think we can use quantum computers? I will give you 3 examples. And they are examples of things we are doing here at CERN, but they are also very much examples of what you can do with quantum computing in general in other fields. So one is the idea of accelerating the optimization problem. What does it mean? You need to choose what is the best possible solution given a set of initial data. Okay? Maybe you want to know, and I'm saying this because this is the exact example that we focused on. Maybe you want to know what is the best configuration in order to focus the trajectory of a beams of particles that runs in an accelerator. This is a very, very difficult task because particles are nasty things. They're not so easy to, focus. What we found out is that we can accelerate and improve this process by using a quantum computer. Another example is simulation. I mentioned this before. Now, all of our experiments are targeted to learn or to understand how the data produced by the collisions work. But we also need a lot of simulation, a lot of synthetic data that we need maybe to understand how our detectors work. Okay, so we do need synthetic data. This is another very, very compute-intensive task. And so this is another avenue that we are learning now we can actually approach with quantum computing. The last example I want to give you is, well, in jargon, would be called pattern recognition. What does it mean? It means that if you have, for example, a cloud of points in space and you want to understand and identify which of these clouds actually belong to trajectory of something you want to trace. For example, you have data in your, control towers from all of the airports in Europe, okay, and you want to understand where each one of the planes are going and where they will go, based maybe on the trajectory they had up until that moment. This is a problem of pattern recognition, and it's actually very similar to what we do in our detector. And so we found out, again, that we could use quantum computing to trace the trajectory of particles through our detectors, and also to trace airplanes in the air traffic control space. So those are very, I really didn't spend that much time on explaining or let's say proving to you that what I'm saying is true. So I really encourage you to ask as many questions as you want. I would be happy to reply. What I want to point out before concluding is the fact that there is a lot of hype around quantum technologies. But there is also a huge, huge promise. And I think it is very important that scientists take the time to try and understand where the impact is, where the real performance can come from, without, getting lost in the hype. This is a responsibility as men and women of science, and I think CERN is really digging very much into it. This is all I wanted to say. Thank you. I got it.
Thank you, Sophia. We're going to get Sophia back on stage after the next talk if you have questions for her. So as you mentioned, there are a handful of directions in which quantum technologies are being developed: sensing, computing, communication. And then there is energy and thermodynamics, which you didn't talk about. And that's still a quite speculative area, but it raises some interesting questions. For example, will quantum technologies change the world's ways of functioning and operating as radically and as massively as the steam engine did in the Victorian era? And I'm not mentioning the Victorian era randomly. I'm mentioning it because last year a book came out with an intriguing title, Quantum Steampunk. Now, steampunk is a genre. It brings together Victorian technology, imagination, industry, philosophy, aesthetics with science fiction. And it allows for exploration of long arcs of science and technology. And the book indeed navigates the secrets of the quantum universe, including the question of whether quantum physics, in addition to transforming computing, may also transform the other big machines of our time, engines. The author of the book is our next speaker. She's a theoretical physicist. She works at the Joint Center for Quantum Information and Computer Science in Maryland, in the United States. She will also help us visualize the quantum entanglement thing that Sophia just talked about. So please me help welcome on stage Nicole Junger-Halpern.
I'm a theoretical physicist. I work in a world of extremes: ultra-low temperatures, ultra-short distances, and in some cases, ultra-fast information processing. So let me take you with me to that world this evening. Let's start with the everyday world. Everyday objects are large, are massive, and contain many, many particles. We call them classical. Quantum physics is non-classical. Quantum physics is the study of very small things, such as single electrons and atoms and particles of light, which are called photons. These systems behave in ways impossible for everyday objects, such as books and microphones and human beings. Quantum systems, as we've been hearing, are notorious for behaving counterintuitively. As Sophia mentioned, a quantum particle can tunnel through walls. A quantum particle can behave in some ways as though it were in multiple places simultaneously. And quantum particles can entangle. The entanglement is a relationship that quantum particles can share and classical particles cannot. Entanglement creates strong correlations useful for quantum computing. If a pair of particles is entangled, you can know everything about the whole while still being ignorant about the parts. Here's a glimpse of how that entanglement works. Let's imagine that some young physicist, let's call her Audrey, has an electron, and her brother Baxter has another electron. The siblings can perform some operation on their particles that creates entanglement between them. Suppose that Audrey measures some property of her particle, and the measurement has two possible outcomes, which I'll call 1 and 0. For instance, Audrey can measure whether her particle has a lot of energy or a little energy. If the two particles are entangled as strongly as possible, then Audrey will have no idea about which outcome she'll obtain. Now, suppose that instead, Audrey measures her particle and Baxter measures his. Now, the two siblings can predict something about the joint outcome. In one example, if Audrey obtains a 1, she'll know that Baxter will obtain a 0. And if Audrey obtains a 0, she'll know that Baxter will obtain a 1. Furthermore, here's the kicker, there is a measurement that the siblings can perform jointly on the pair of particles together, such that they can predict the outcome with certainty in advance. So there's something, some information that isn't in Audrey's particle, it isn't in Baxter's particle, and it isn't even in the sum of the two particles addressed independently. It's spread across the pair. Or when it comes to entanglement, the whole really is greater than the sum of its parts. Scientists and engineers are now leveraging entanglement in quantum information science. But let's start with ordinary information science. Across science, we measure quantities in units, such as seconds and meters. The basic unit of information is called bit. 1 bit gives us the ability to distinguish between two possible alternatives, such as, yes, I will marry you, and no, I won't marry you. You can store a bit in a physical system that's in one of two possible configurations, such as a thumb that's pointing upward or downward, or in our classical computers, in a transistor that has the value 1 or the value 0. The basic unit of quantum information is a quantum bit or a qubit. Now, we can gain information from a bit by asking one yes or no question, such as, will you marry me? We can gain information from a qubit by asking any of infinitely many yes or no questions. So a qubit has, in some sense, the capacity to encode more or at least different information than a bit. Quantum information science is the study of how we can use quantum phenomena to process information in ways forbidden for classical systems. Quantum information technologies, as we've heard, include quantum computers, networks for communication, cryptographic systems, and more. Quantum computers will be able to solve in minutes specific problems that would take even classical supercomputers many years. Today's quantum computers, while they exist, are small and very limited. Errors corrupt the computations constantly. The experimentalists' next big goal is to implement error correction, which will require significant advances in hardware. So many of us in the field expect that it will take quite a few more years to build quantum computers up to their full potential. But an important application of quantum computers will be to research and development in material science and chemistry. One example concerns energy use. We invest about 3% of the world's entire energy output in fertilizer production. Why do we spend so much energy? Because we used an old technique from 1909. Bacteria, it turns out, can accomplish the same goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. But the molecule is quantum. So a quantum computer can naturally be better suited to unlocking the molecule's secrets. Now, this is not a quantum computer, although it looks cool enough to be one, doesn't it? This holds a quantum computer which fits on a small chip. The chip needs to be at low temperatures to support quantum phenomena such as entanglement, which are destroyed by heat. So this device cools the quantum computer to temperatures lower than that of outer space. So this device is called a dilution refrigerator, or to those of us in the field, a fridge. Yeah, so actually, when my husband heard that, he's a classical computer scientist, he was kind of indignant. He said, so this cools things down to below the temperature of outer space, and you don't even call it a freezer? Anyway, the importance of cooling leads us to the importance of energy science, called thermodynamics. Thermodynamics is the study of energy, the different forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in two forms: heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized energy, and so isn't directly useful. Work is coordinated energy that can be directly harnessed to power a factory, or charge a battery, or raise an anchor. Heat engines convert random heat into coordinated work. Heat engines drove the Industrial Revolution by powering the first factories. So people started wanting to know how efficiently these engines could operate. So they developed the theory of thermodynamics during the 1800s, the Victorian era, giving the theory a practical spirit. However, the practical questions led to fundamental questions like, why does time flow in only one direction? Thermodynamic tasks include cooling and powering and charging. They echo information processing tasks such as computing and encryption. Now, we've seen that quantum phenomena such as entanglement can enhance information processing tasks. So can they enhance thermodynamic tasks? How would quantum engines look, and what could they achieve? More generally, how can we extend the Victorian theory of thermodynamics from large classical systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, my field of research. Here's an example of what we can uncover at this intersection of quantum information science and thermodynamics. We'll see that an information processing task, erasure, costs thermodynamic work classically. But given entanglement, instead of spending work to erase, we can obtain work. We can store a bit not only in a transistor, but also in a gas particle in a box. Suppose that this particle is classical, like a miniature basketball. If the gas is on the box's right-hand side, we'll say that it encodes a 1. If the gas is on the left-hand side, we'll say that it encodes a 0. That's the bit. Suppose that we have no idea where the particle is. It can be anywhere in the box. Its position is totally random. Suppose that we want to reset the particle's position to the box's right-hand side. So a nice, clean state. This is like taking a messy sheet of scrap paper that's been scribbled on totally randomly and erasing it to a nice, clean state. To erase the bit encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature, through the box's walls. Then we slide a partition into the box near the left-hand wall and push the partition to the box's center. The gas ends up trapped in the right-hand side. At what cost? We compress the gas, so we have to exert energy, namely work, the coordinated, useful type of energy that can be transferred between systems. So we spend work to reset the particle's position or to erase the bit of information. In other words, erasure, an information processing task, costs work, a thermodynamic resource. This statement is true even of the most energy-efficient classical computer imaginable. And what if we add quantum physics to this mix of information and energy? Well, the story can change in multiple ways. I'll share one way discovered by colleagues of mine, including the Portuguese physicist Lydia Del Rio. Suppose that we want to erase not a classical bit of information, but a qubit. We can store a qubit in Audrey's electron from a few minutes ago. Now, Audrey's electron can be entangled with Baxter's electron in some fixed temperature environment. My colleagues proved that Audrey can erase her particle's information while gaining work that she could use to charge a battery or lift a really tiny weight. This result should surprise us. We just concluded that we have to spend work to erase information. The trick is to sort of burn the correlations between the particles. Entanglement and heat together serve as a kind of thermodynamic fuel. So quantum phenomena, such as entanglement, can serve as resources in thermodynamics, in gaining work, as well as in information processing. Beyond erasing information, we can build quantum thermodynamic engines, refrigerators, ratchets, and batteries. Quantum phenomena can benefit these devices, my community has found. We can use entanglement as a resource in refrigeration. We can charge quantum batteries at a greater power if we entangle them than if we don't. One of these quantum engines that burns, so to speak, information can perform more work on average than its classical counterpart. And quantum engines can operate under conditions in which classical engines cannot. These results not only help us extend Victorian thermodynamics into the 21st century, but also shed new light on what distinguishes the quantum world from the classical. Quantum thermodynamics reaches back to the past, to the 1800s, and ahead to the future, to quantum computing. So does steampunk, a genre of literature, art, and film, reach back to the past and ahead to the future. Steampunk stories take place in the 19th century. Some of the earliest factories are belching smoke. London is full of smog and Sherlock Holmesian mysteries. Paris is in La Belle Epoque, and people wear waistcoats or petticoats. Against these backdrops are futuristic technologies: automata, time machines, flying ships, and submarines. The Canadian poet Douglas Featherling has supposedly said, "Steampunk is a genre that imagines how different the past might have been had the future come earlier." You might have encountered this steampunk novel, The Time Machine, by H.G. Wells. It's one of the first steampunk works. It was written during the 1800s. But steampunk is very much with us still. The Invention of Hugo Cabret was a bestseller in the early 2000s. Enola Holmes was one of the first films released on Netflix due to the pandemic. It follows Sherlock Holmes' little sister, who's called Enola. I loved the film. This fusion of old and new creates a wonderful sense of nostalgia and adventure, romance, and exploration. So fans dress up in these steampunk costumes with top hats and goggles and gears and gather at steampunk conventions, for the sake of a fantasy. But this fantasy of steampunk is becoming a reality in quantum thermodynamics. So I call this field quantum steampunk. When I was a student, I read about steampunk in a novel. At the beginning of the pandemic, I saw steampunk in a movie. But this genre of fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. So the fantasy of steampunk is becoming reality. Thank you.
Thank you, Nicole. Let's get Sophia back on stage as well. Yeah. And we have microphones for you as well in a couple of minutes. But Nicole, you mentioned the idea that the energy surrounding entangled particles can be used to lift small weights. Can I use it to charge my phone?
Not quite yet. At the moment, quantum thermodynamics has been at the stage of fundamental discovery, and we're now starting to pivot toward practical applications. For instance, I recently collaborated with a lab in Sweden on a quantum refrigerator that would actually assist a quantum computer. So after a quantum computer has performed a computation, the qubits are used up, they need to be cooled down even more, and this quantum refrigerator can do that, according to one metric, better than some of the best known techniques.
Now, when we think about things like quantum engines and batteries, what is the time horizon to make them practical, usable elements of, I wouldn't say daily life, but our current reality?
I probably shouldn't make a prediction about timelines, but this first practical experiment that I mentioned happened last fall. It was performed by an experimentalist at a university that is building a quantum computer from superconducting qubits, so very cold quantum circuits. And we came up with this idea in part because he said it could be useful for him and his colleagues as they are building and using this quantum computer.
Sophia, you work in quantum, but you also work on artificial intelligence and machine learning. Tell us about the bridges between the two.
That's a very nice question. So the point is that for many years, the first algorithms quantum algorithms that people started to know and try to use proved that you could actually accelerate the algebra very, very easily, or with very much. And most of what you do in machine learning, at least classical machine learning, the way we used to do it a few years ago, not ChatGPT today, just so we're clear, that's mostly algebra. And so very early on, people started to think, okay, maybe we can use quantum computer to speed up machine learning. Now, the point is that machine learning is actually useful when you can run it on a lot of data. And that's actually something that we cannot do so easily today on quantum computers, mostly because of the limitations that computers have now, their size, and all the engineering that's needed to actually load classical data on a quantum state. So this is a very big challenge. But other than that, there are other things that quantum computing can do for machine learning. And one of the things that is, I think it's most fascinating is the fact that because we are using quantum state and because we are building systems that learn how to describe the data in a quantum space, then you can think of building models that are more powerful, okay, that are able to represent data sets that are more complex than what you could with a classical network. So there's two aspects. I would just like to say that this is something that already exists. So it's not something for which we need to wait a long time.
So you mentioned before the future collider of CERN, which is going to be much larger in size, but also much more productive in data.
Yes.
It's gonna create huge amounts of data, which don't seem to be manageable with current technologies. So you said that we are looking into quantum as one possibility for that, with other potential options. But will the technology arrive fast enough?
So the next generation LHC is actually very close in time. We are talking about 2030 something. So, right, this is called the high luminosity LHC. It is unlikely that we will be able to solve problems at the LHC using a quantum computer, at least at the scale we are thinking of people typically think of.
So what you're
You
saying
could
is quantum is developing much
It's a
more
longer
slowly.
time
Yeah.
scale, or we need to think of it for very specific problems. That is something we will be able to do.
Okay. Let's see if we have some questions from you here in the audience. So
I don't see.
there's a hand raised right there. Can we get keep your hand up so she can see you? Yes. Stand up and ask your question, please.
Hello.
Now we go.
Okay,
Good.
it's a question for Sofia. My name is Marco Palumbo. I work for Inflection. We are also a quantum computing a company. So the question is about the vision for CERN. Do you, as a user of quantum computers, will you be building one?
Okay.
If you're gonna be build
Yes.
one, which platform are you gonna go for?
I can tell you right away, we're not going to build a quantum computer, at least not in the next QDI phase, but we are going, so this all work started for us as users. Now we are also very well aware of the fact that a lot of the things we do at CERN are expertise that we can use to improve quantum technologies. So that is something that we want to do. So we are going to study systems of qubits. We are going to study how, for example, to improve the way we read information out of them, for example. We are going to study how we can characterize their behavior, to understand how stable they are, to understand how to best account for these problems that are related to the technology still and the fact that it's a quantum state. But our main goal is to understand the relationship between quantum and physics and high energy physics. This is the core of the investigation.
Yeah, no, thanks. That makes sense. Are you working mostly with the superconducting people? Are you testing, across?
Yeah. So there are. So this is. I'm not sure how clear it is. The fact that there are many different ways you can build qubits. You can build quantum computers. Nicole very nicely explained to you what is the concept behind the qubit. So there are many different technologies. Superconductors are a way of building qubits. We are working on we are using superconducting computers, but we're not necessarily going to focus on that technology only. And the reason is that the technology is developing very rapidly. There are many different options, and there are advantages and disadvantages at looking at different approaches to qubits, let's say it that way. And there are also advantages depending on the task that you have in mind. One specific technology could be better suited to solve a specific problem. And so we don't want to focus on only one direction.
Is there one more question? We have time for another question. Not the case. Yes, here. Wait for the microphone, stand up.
Shout.
Does it work? Okay.
Yeah.
Okay, I'm a regular university student, so maybe my question will not be on level, but I have a question for Nicole that was talking about the quantum fridge and quantum batteries and all those stuff. If I understood correctly, they need to work the entanglement phenomenon, no? To produce the information that gets deleted to get the work.
Some of them do. There are lots of different quantum phenomena, such as superpositions, entanglement, even more things that we didn't talk about. And some of these technologies do take advantage of entanglement.
Okay, so, but the thing is that I guess that to get to the low temperatures needed for this phenomena to take, to appear, you need to use a lot of energy in the first place, no? To get to those low temperatures. So how can you get then a net positive work to process something else?
Yes, that's one of the reasons why I said that you can't at the moment use quantum engines to charge your phone. So far, we have done a few things. We've designed quantum engines and other quantum thermal machines and shown that according to some metrics, they can outperform their classical counterparts. This is very fundamental work. Then, in part because I wrote that book and had this conversation with this experimentalist I mentioned, we started thinking more about really how to take these quantum thermal machines that are great in principle and make them actually more useful, more in the spirit of the Industrial Revolution. So we recently embarked on this research program of autonomous quantum machines. this quantum refrigerator is going to be placed inside one of those giant refrigerators that I showed you. That will already be cold because, for example, these folks at this university in Sweden want to perform a quantum computation. So if you stick your quantum refrigerator inside of that refrigerator, the classical refrigerator, it'll already be cold. You won't have to spend you'll have to spend negligible extra energy on cooling down your quantum refrigerator. And then we can give it access to kind of a free energy source, just basically via surroundings, so that it can kind of extract its own energy in order to cool down the qubits. So we're looking for these very specific situations in which we have an environment that's already cold, and we can just slide a quantum thermal machine in there, like this refrigerator, that will do its own thing. So far, we have this application, and we're looking into more, as well as other research groups around the world.
We're going to come back to the question of energy use after the next talk. Okay?
Thank you.
Thank you. Nicole, Sophia, thank you very much.
Thank you. Thanks for the question.
Good evening, everyone. What a pleasure to be here. A philosopher at CERN. I think that's a great place to meet. I'm very excited to dive with you into the world of quantum computing, into why we build and develop quantum computers, what we use them for, how they work, and also how we can make sure that as society we can use them in a way that we all can profit from them. So, as you know, as society as a whole, we have a number of tremendous challenges that we're facing, from feeding the world, feeding the world's population, the climate crisis, better stable markets, better financial markets, to drug discovery, something that is currently relatively slow, as we unfortunately had to experience over the last years. These problems are so challenging because they're incredibly complex. They're actually so complex that with our classical computers, they're coming to the limits. And as you know, the classical computers that we're having, they're huge. So there's something about these types of problems that makes them specific, that with our classical computers, some of them we can't even address just by the nature of how some of them work, so just by the nature of how nature works. So to look a little bit closer into the kinds of problems, what they are, and which ones we can address and which ones we can't address, I find this graphic really helpful. So if you think of all the types of problems that we're having, the types of problems that we can address today with classical computers are in the middle. Those are the white problems. As you can see, it's a relatively small subset. Then there's a huge type area of problems in the light blue, which are the problems that we can't address adequately today. And then there's the blue ellipses, which is the types of problems that we hope to be able to address with quantum computers. And it's not because I'm really bad at PowerPoint that the ellipses actually spans into the dark, but it spans into the dark because there might be a type of problem that we can't even think of today that we will be able to address with quantum computers. So you've seen that there really is a number of large complex problems that we hope to address with quantum computers. So what might these be? I can tell you the numbers in the white, in the middle in the white, the types of problems are things like writing emails, number crunching, potentially streaming Netflix, rewatching this talk at some point. But the types of problems that are in the dark blue are problems like this. So they range from simulating quantum systems. As we know, nature doesn't behave according to the laws of classical physics, it behaves according to the laws of quantum physics. So with classical computers, we cannot simulate nature accurately. We do need quantum computers for that. So that's one big area, and that spans to areas such as quantum chemistry, material sciences, and high energy physics, a place that we find us in here. There's also potential applications in the area of artificial intelligence, where we can potentially do better model training, pattern recognition, and also in the area of optimization. As you know, optimization problems are very, very challenging problems, and so doing those optimization problems faster has huge potentials. But okay, seeing what we could do with quantum computers, and what classical computers aren't adequate for, of course, this raises the question, well, what is it then about quantum computers that makes them so special? The answer, the basic principles of the answers lies in this two sides of the graphic. On the one hand side, you see what we call a qubit. So you know that in classical computing, we compute with bits. Bits, we can represent information in the form of 1 and 0. But with qubits, we can harness the principles of quantum physics and can actually represent not only 1 and 0, but also 1 and 0 at the same time. So 1 and 0 at the same time, that uses the principle of superposition. What is that? How might that work? There's a nice analogy that you can use to think of it. Think of tossing a coin. You have the coin on your hand, on the palm of your hand, and there you measure it. It's either 0 or 1. Then you throw it into the air, and while it's in the air, you can't tell, is it 0 or 1? It's in a state of superposition, you could say. When it lands back in your hand, it's again either 0 or 1, or either heads or tails in that case, and so you've measured it. And you can think of it similarly when you hear superposition, it's a similar principle. And so we can actually encode information in those states. So with a qubit, we have twice the amount of information that we can encode, and if we add multiple qubits to another, which we're doing in a quantum circuit, then this phenomenon actually grows exponentially. And since the past 2 years, I don't have to explain exponential growth to you anymore. So you can imagine what exponential power we're having in using quantum computers and harnessing some of the principles of quantum physics, such as superposition, entanglement, and of course more. The question then is, well, how can we control these qubits? Because in order to calculate with them, such as with classical computers, we need to control them and also tell them how to actually calculate with them. And this is what we call quantum circuits. It's another term for just a quantum algorithm. So we put them in a certain order, we tell them certain ways to behave, and then we can measure them at the end. And this is how we then read out our measurements and the result of our calculation. So this is the basic principles of quantum computing, and don't worry, this is not going to go into a lecture, but gives you some of the basic principles that allows you to understand why they're so powerful and why we're so excited about them. So the next question then, of course, is, well, okay, that sounds fine, but where are we? Is that theory? Do we have them? What's the road ahead? And you're noticing that we're really exploring uncharted territories here. And for any exploration, typically what you take with you is a map. And typically this map also looks relatively messy because it has a lot of details on the map. So I've brought with you a map that we're using to explore the territory of quantum. And as promised, it looks a little bit messy, or at least very busy. But don't worry, we'll go through it in detail, or I'll help you how to read this map. So start at the bottom in the dark blue. This is where you can see the hardware. So you see one of the qubits, or actually in the first one you see 27 qubits on a chip. This is what we started with 2019. This is actually when we put the first quantum computer on the cloud. So if you had tried to use a quantum computer in 2019, you could have used them via cloud. And then since then, we've progressed. And if you go to the top, you see the timeline. And so you see that in 2022, we've released a 433 qubit system. So you see that the systems are growing. The number of qubits on the chips are growing. And then you can see also from today, 2023, 2024, and to beyond 2026. What you can see, and what I want to draw your attention to as well, is to the top. You can see that starting this year, we're really entering the era of utility quantum computing. So we're entering the era where we can use quantum computing for useful scientific discoveries. We're entering the era, we're at the beginning, that's very important to mention. But you can see that also as we're growing the systems and making significant advances in the middleware, and I won't go into detail there, we really are getting towards further advancements on all of the levels. So when you wonder, where are we with quantum computing, what's the map or what's the roadmap ahead, think of something like this. And this is actually publicly available, and we're accountable to it. And so far, we've achieved every step of it. So it seems to be a reliable map as well. So I've shown you sort of a picture of a qubit, what it might look like, but I also want to show you what a qubit and what qubits actually look like on a chip. So the chip that we've released last year, this is Osprey, is a 433 qubit chip, and you can think of it looking like this if you kind of opened it up and looked at it from the side. And this is you can see the architecture and how the qubits are arranged on that chip. But often when you hear about quantum computing, you hear, and it's very impressive also, the number of qubits on a chip. I mean, consider that this chip is just a tiny bit larger than a penny coin. So it's very, very impressive. However, there's other elements that you need to bear in mind when you're considering the performance of a quantum computer. And this is something I would really ask you to take away with you, because often we get stuck in conversations about quantum computers and the number of qubits. But really what matters is, on the one hand, the scale, the number of quantum qubits, but how these qubits behave. As we're cooling down our quantum computers to minus 270 degrees, so to colder than outer space, we're already doing quite a lot for them to behave, to control them. But they still do misbehave at times. So we need something, we need the quality, we have a measure for a quality, which is about the fidelity of the qubits and the circuits as well. And then, of course, as you know, with any computation, there's speed. You don't want to run a computation, wait forever, and just get bored waiting forever. So those are the three aspects you should actually look at when you're wondering, where are we with quantum computers? Are they good quantum computers? So going back to why do we build them? So I've told you we have a number of complex problems. I've told you only a few, maybe the most important ones, maybe not, but a few really, really important ones that as a society we're grappling with. And I want to focus on the one in drug discovery and in healthcare and life sciences. So you heard that quantum computers can simulate nature. So naturally, it's natural to think of, okay, where do we simulating nature that's in the area of healthcare and life sciences? And there is institutions such as hospitals that also do research. One of the largest ones actually is in the United States, is Cleveland Clinic. It's a very large institution that does research, but also is a hospital itself. The Cleveland Clinic is known to be an institution that does leading healthcare and life sciences research, and also to do education. And they decided that if they want to be ahead and be able to continue driving the research in the area of healthcare and life sciences, they also need to be ahead with technologies. So actually, Cleveland Clinic has decided to buy a quantum computer. And this is not science fiction. They've not only decided to buy a quantum computer, they've also actually already installed the quantum computer. So if you walk to the cafeteria of the Cleveland Clinic, you can see this. So there's a working quantum computer with 127 qubits, and they'll get the larger chip as well, that they use for their research, and they also use for educational purposes. So the types of problems they're looking into are very similar to the types of problems that I've discussed before. They're simulating nature, so for drug discovery, for diagnostics, for precision medicine, processing large complex data, and of course also search and optimization. And you have those also in healthcare process optimization or population health management. So this is in the area of healthcare and life sciences, and it's very much happening right now over in the United States. Another area that challenges us is the climate crisis. And as we know, we're trying to move away from traditional cars to electric vehicles. But we also know that one of the challenges is that with electric vehicles, the grids actually, that they're peaking because we're charging them overnight, and so we have peaks in the usage of the energy, and that's not ideal. And as an energy supplier, and one of them is E.ON, you might have heard of, they're really interested in having an optimized way of how the energy is distributed across the grid. And so they're actually looking into using quantum. This is an incredibly complex operation, an incredibly complex optimization problem. So they're looking into using quantum computers to see whether they can optimize the way that energy is being used in the grids. Another that is also related to the climate change and also in some way related to electric vehicles and using more batteries is from this car manufacturer. You might know that batteries currently, they're very heavy, they don't last as long as we would like them to, so they need to be lighter and last much longer, and for that we need to discover new materials. And so this company is looking into discovering new materials with quantum computing. So again, we're going back to simulating nature to see whether there's better materials for the use in batteries. So I think this makes really clear what the potential of quantum computing is, and that the prospect of being able to address these really challenging problems is really fascinating. However, there's one challenge that we have as a globe, and that is who has access to quantum computing, who partakes in the research of quantum computing, and ultimately also who will benefit from these tremendous benefits that I think we would all want to benefit from. If we look at who currently invests into quantum computing and who currently across the globe has a quantum computing strategy, we see something like this picture. And as you can see, the picture is colored very heavily on one side of the globe and not so much on another side of the globe. And this is a challenge, I mean, that we're seeing with digitalization in general and the risk that we're seeing with quantum. The good thing is that with quantum, we're early on. So with quantum, we're so early on that we actually can do things differently. And this is why we're doing research into responsible quantum computing. So responsible computing, understood as computing that is considering the implications of the technology, that is aware of the power of its effects, that is looking into mitigating the potential harms of quantum computing proactively in an inclusive manner, looking into accessibility and accountability, and so overall to be guided by principles of responsible technology development. And this is really, as I mentioned, we're really early on, so we're at the beginning of the era of quantum computing. So it's really, really high time that we think about this because we can be proactive. With other technologies, we're running behind. We had to see what had to go wrong first, and then we come up with solutions. With quantum computing, we have the opportunity to really learn from that and to not make mistakes again. So we can be really proactive. And also everyone in the community, we're all working on this because we want quantum to be used for good. None of us is working on this, and there's a lot of hard work, as you can imagine, being put into this. None of us do this so that they're misused. So as a community, we're really interested in also having quantum computers used in a very responsible way. And we also finally have as a moral philosopher, we have the moral obligation also to do so, to consider the implications, to consider what is happening outside of the lab. And fortunately, I'm speaking today at CERN because there's actually a wonderful initiative that was born not far away from here at Jester and is now hosted at CERN, which is the Open Quantum Institute. The Open Quantum Institute that was just announced very recently, or launched very recently, about a month ago, has the mission to make quantum computing accessible for everyone, to grow education, to grow the awareness, especially also among policymakers, and to make sure that in addressing these most complex problems, we're addressing those that have already been identified as being the most complex problems, namely those that we're addressing within the SDGs. So this is a very real initiative that is happening, that is starting to address the challenge that I've mentioned. So coming to conclude, you've seen that with quantum computing, there's a lot of potential. We can improve nitrogen fixation for creating ammonia-based fertilizers. We can potentially find new materials to better store carbon. We can find better financial models for more improved financial markets. And we can discover new classes of antibiotics, new classes of drugs that we urgently need. If you now think, well, this sounds a lot of the future, this sounds very rosy, then I'll just leave you with this. Then I think you're thinking too classically.
Thank you, Mira. You showed us this chart that is now somewhere between 500 and 1,000 qubits for a computer, right? That's the current state of the art. When we think of a really powerful quantum computer, we're talking about millions of qubits. So what are the bottlenecks that we need to break through before getting there?
Yeah, so I've alluded to one of them, which is the way that the qubits behave. So although we already cool them down, we call that them being noisy, which effectively we mean that they don't quite behave the way we want them to. And so not only do we have to build larger systems, but we also need to build larger systems that are more reliable. So that's why I mentioned the fidelity. And so that is an engineering challenge that we need to overcome. So it's really one where we need breakthroughs, and we're making breakthroughs on a sort of daily basis to overcome this engineering challenge. Another challenge then also is in making sure that when we're using quantum computers, we're finding the right problems to use them for now. So we're partnering with a lot of institutions to make sure that as we have these as we're sort of chartering into those territories and as we're starting to be able to really use them, that we're using them at that moment for the right problems and not using them for something that is not actually relevant.
How flexible is a quantum computer? I mean, what I understand is it's not updatable, for example. If I buy one now and I put it in my cafeteria, it looks cool, no doubt it looks cool, I will impress my friends, but I cannot just download another piece of software in 6 months and update it. So how specific are they to specific tasks?
No, so we're building so the aim is to build universal fault tolerant on quantum computers. So there's a lot of work going on, of course, with the software and the middleware to improve that. But it's kind of, I think you need to change the way you ask that question as well, and because you come with a problem that is relevant for a quantum computer, and so you need to, of course, address it in ways, or kind of put it in ways that it can be run on a quantum computer, and then you can run it. So you use a different software. It's a software, for instance, we call Qiskit. It's an open source software as well that you can use. But yeah, you need to kind of make sure you've found a problem. So if you came and wanted to crunch numbers or write emails with a quantum computer, I hope someone would tell you very early on to not do that.
Not do that. Just out of curiosity, the quantum computer we saw from Cleveland, what's the price range for a machine like that?
I work in research. I don't sell these things. Wrong person to ask.
I suspect it's in the several million. But going back to the question that he had before, so there is the aspect of using quantum computers to optimize, for example, electric distribution, etc., etc. There is also the aspect of quantum computers using a lot of resources and energy, right? The machine we saw is probably, I don't know, 3 cubic meters in size, but the actual computer is something like this.
Yeah.
So all the rest is wiring, cooling, and supporting machinery. We've heard a lot in the last year and a half since ChatGPT and other AI systems came into the public space that the energy use of data centers and AI is growing exponentially. What is the game here in terms of energy use?
So there's sort of two parts. The reason that we're looking into using quantum computers for optimization problems or for simulation is so that we can actually run these types of problems that we're currently running on sort of inefficient classical hardware, that we can run them more efficiently. That's one part. And the second part is also, so we're looking for quantum advantage. So we're looking for when a quantum computer has an advantage in solving a problem over a classical computer. But there's also an initiative that is looking into quantum energy advantage. So the idea here is to create a benchmark where not only we're looking that a problem is being solved faster, but also that it's being solved in a more energy efficient way. And so this is actually something that I think most of the community is currently looking at and doing active research into, because of course the question is, as quantum computers will run in sync with classical computers, so you can't think of one or the other, you will use them together. So the question is, if you want to measure that and benchmark that, where do you start? Do you kind of dissolve the quantum calculation from the classical calculation? Do you take it from start to the end? And so it's currently a very active research to look into how do we measure that, how we actually say how much energy is being used. And so this is an initiative that's actually not far from here, from Grenoble, from the CNRS, that's called the Quantum Energy Initiative, that is looking into establishing exactly that and how to measure that.
Mm-hmm. Okay, it was the same question, and you have a question. Please stand up.
Hi.
Yeah, it's okay.
Really happy that you gave the example of financial markets potentially using quantum technology. So I know that banks, in some cases, are quite dependent still on legacy systems for various reasons. So for these institutions to effectively leverage quantum technology, what kind of changes are you expecting to see at like an enterprise operating model for these banks to be able to effectively use this? And like on a high level, how would you go about building a capability to use quantum data analytics, for example?
Yeah, I think that's a very excellent question. So I'll try to be quick in the how. We could talk hours about this question. But basically, so the important sort of underlying assumption is that with quantum, it's going to be integrated into the IT infrastructure. So ideally, as an end user who's not responsible for running who's not sort of at the quantum computer and making sure the integration is happening, you're not really noticing. You don't have to necessarily know, is this being run on classical or is this being run on quantum? However, at this point in time, when you're trying to integrate, you're trying to also find out what are the most relevant problems. It is really, and this is something we're seeing happening, it's on upskilling. So I mentioned that there's a certain software, which is Qiskit, and it's on learning this. And so the how is to starting right now on upskilling to understand how to transfer your problem into a problem that can be run on a quantum computer, and to really start with small problems that you can use the machines for now. I mean, every bank could log onto the cloud and use them right now, and to then, when we have the larger systems, to really be able to harness the potential. And so, yeah, I think that this is something sort of it's really across awareness building, so that the entirety of financial institutions also understand what the relevance is and can use it the moment the systems are at the utility scale.
From the mainframe to the quantum computer in a single leap. Okay, Mira, thank you very much.
Right now.
Thank you. So let's get even more concrete. One possible measure of the growth in quantum research and development is, of course, the measure of everything, which is money. This year is calculated that about $40 billion will have been invested in quantum research and development by the end of the year. Some of it comes from big companies like IBM or Google or others, and some of it comes from national initiatives. The most ambitious are the Chinese, the Americans, the Germans, the French, and the British. Switzerland has a very tiny program, 10 or 11 million francs. The others are in the half or more than 1 billion. So to help understand a bit the landscape of quantum development and strategies from the perspective of the government's funding that research, we invited the head of quantum tech policy for the UK government's national quantum strategies. She's joining us now from London. Let's see if Rachel Mays is online. Rachel, welcome.
Good evening.
Thank you for being with us. I hope things are good in London. So, in the UK, quantum is defined as one of 5 priority fields for the Department of Science, Innovation and Technology. The others are AI and synthetic biology and things like that. Why quantum should be a priority for a government, and why now?
Well, I think the speakers before me have actually set out a pretty good case for why quantum, but maybe just to build on that. So the 5 critical technologies are really based on government's assessment of the technologies that are underpinning, really enabling of wider innovation. So they're both disruptive in their own right, but they enable innovation across the economy. So, you know, I think you've heard about the exponential increase in computing power, you know, to allow us to solve intractable problems. We also are interested in quantum sensing, timing, and communications, which have other advantages. So I think in terms of why now, yes, quantum computing may be a few years away, but as you've heard, actually, you need to start engaging with it now to really be aware of where it may have a benefit for you, to upskill and to explore potential application areas, because that will actually inform the development and make sure that people are ready for quantum, for the for using scalable machines when they are here.
So the UK program is about 10 years old. This has just been renewed for another 10 years. Give us a sense of how it is shaped and structured, and how much money is the UK government putting into it?
So you're right, we've had a quantum program since about 2014, so that 10-year, 1 billion investment is coming to an end next year. And we are starting a new program for the next 10 years, investing 2.5 billion. So the program for the last 10 years really started with the hubs, which brought together the scientific communities in the UK, created really a hub of activity to bring people together around a program of research and technology development, working with industry and government. We built on that in the second phase, so the last 5 years of the first program, bringing in challenge funding, which is industry demand-led, so really starting to explore between academia and industry, what are the feasible applications of these technologies, how can we build supply chains? And then more recently, we established a National Quantum Computing Centre in recognition of the fact that computing is quite unique and has quite significant challenges in terms of scaling and creating an entirely novel computing systems with novel hardware, control systems, software layers. So the NQCC helps to provide that linkages between the system and help users explore use cases. So looking forward to the next 10 years, we are really building up the adoption phase of the program. And that means we are looking at government procurement and setting quite high-level missions and outcomes around societal benefits. So we're moving more towards helping government and key sectors adopt these technologies in the coming years.
So out of all the spectrum of potential applications, the one that have been developed now and the one that are just imagined, which are the one or two that excite you most?
Gosh, what a what a question. It's like choosing your favorite child. I think there are so many potential applications. Yes, I think some have already been mentioned around, drug discovery is a really exciting area. So maybe it's helpful to talk about some projects we're funding, which are looking at grid optimization, which I think has already been mentioned, optimization of public health services. There are so many potential areas to explore that have benefits for society and, real economic benefits. So yes, I don't think I could choose one particular one.
So you mentioned before collaborating with the industry. I assume you're also collaborating with other national programs.
Yes, that's right. So, this is an international endeavour and no one country can do this alone. The UK works very closely with many different countries. And I think, it's going to be really important to enable international collaboration on both research and to build the industry and the supply chain to really, help this industry scale and become established and mature in the future.
So a couple of weeks ago, the UK hosted a big international conference at Bletchley Park on regulating AI. It was kind of the first of its kind. There have been going to be more also in other parts of the world. The UK Quantum Plan also says that the UK wants to be a leader in discussing the regulation and the ethical implication of quantum technologies. What's the vision there?
Yes, the UK was very excited, proud to host that summit. And for quantum, I think we're a way away from where we are with AI, but we can learn a lot from that experience. So in the UK, we have asked the Regulatory Horizons Council, which is an independent advisory group of experts who are experts in regulating technologies, and they are doing a review of regulation for quantum. So we are expecting them to report fairly imminently, and I think people do have this argument about, is it too soon to regulate for quantum? And I think it's never too soon to start to talk about and discuss, debate and understand the applications and therefore the implications of these technologies and start to provide, the frameworks, the principles, the standards, the taxonomies at this stage so that you're anticipating as much as you can. I think that the important thing is, not to regulate too early and stifle innovation and research, but also, quantum technology spans so many different areas. It's quite hard to regulate a technology. So quite often, the regulation will be through the application itself, I suspect.
Yeah. Just to stay for a second with the parallel to AI, there is a lot of concern about AI wiping out a lot of jobs, etc. There may be some concerns about quantum computing having another effect on another. Oh, did we lose Rachel? Please tell me something from up there. She's still here. Excellent. Rachel, do you still hear me? Excellent. Sorry, there was a moment of... So, okay, let's see. We are good?
Yeah.
Can somebody say thumbs up, thumbs down? We are good. Okay, excellent. Rachel, let me then reframe them. There is a lot of concern about quantum computers being so overwhelmingly powerful compared to today's computers that they may wipe out a central element of how the economy works today, which is secure computing, secure communication, secure data management. So cracking all existing cryptography, for example. How do you look at that from a policy standpoint?
So from a UK perspective, the Technical Authority for Cyber is the National Cybersecurity Centre in the UK, but they have done a lot of analysis and policy development around responding to that threat. So I think it is a very real threat, but there are things that companies and governments can do today to help protect against that. So there are existing mechanisms that are safe, and then NIST and others internationally are developing quantum-safe algorithms. So once they are developed, the plan is really they will be rolled out globally and will provide protections that are necessary. So I think many governments have their own advice to industry and for use in government systems. So we have a white paper that sets out really what people should be doing to protect themselves both now and going forwards.
So you mentioned before international cooperation. We live in a time of fragmenting international collaboration, and yet it's definitely essential for the safe development of these technologies. How do you balance competition and collaboration at an international level?
That's quite a question. So I think from a policy perspective, this is not new for quantum. This issue has been around for many years. So I think, globally we need to work together across different countries really to make sure that we're still enabling research to happen, that we help businesses to work across borders. And I think there will always be competition. I think what we are seeing or have seen in the last few years is increasing protectionism amongst many states towards critical technologies like quantum. And I think it will be very important to keep an eye on that balance and make sure that we're not stifling innovation before we've even got the technology in the first place. So yeah, that's not the full answer for you, but I think a bit of a steer through. And it's important that countries do work together and start to look at the global supply chains and having a trusted supply and market and industry in the future.
So about a month ago in Geneva, the Open Quantum Institute was launched, and the idea is to create a neutral platform to ensure equal opportunity globally in accessing and in using quantum technologies of any kind in the future. How do you look at the Open Quantum Institute?
So I think this is a fantastic initiative. So the UK is very supportive of it. In the quantum strategy that we published back in March, we have a commitment to, dedicate, I think it's 30% of, NQCC time towards exploring applications that have a societal benefit. And, we have already set up mechanisms to do that in the UK through the Catalyst Fund that I referred to earlier, which is a mechanism to enable people in policy to work with companies to explore a particular use case that has a public benefit. So I'm very supportive of the initiative and look forward to hearing more about how that's going to be how it will be realized in the coming years.
Rachel, thank you for taking the time and sharing your knowledge with us, and enjoy the rest of the evening in London. Thank you very much. Rachel Mays.
Thank you. Thanks.
I was watching at that clock above our head. It feels like it's entangled with some clock that's in repair somewhere in Geneva or somewhere. So we've discussed quantum from the points of view of science, of business, of policymaking. What about art? Artists also have a point of view on science and also on quantum technologies. What about our own perceptions of this technology and the perception of artists, and how do they turn it into artworks? So some of you may know, and some others may be surprised by the fact that CERN, biggest research center in particle physics in the world, looking at the universe, also has an art project. It's called Art at CERN. It's hosted here. It invites artists in to stay in residency for several weeks to talk with physicists, to use the data from the accelerator to explore ways to turn those data into artworks and exhibitions. And in 2016, the artist in residence, with the support of the Ministry of Culture of her home of Taiwan, was the dancer, choreographer, and new media explorer Wenqi Su. In the meantime, she has created a series of works inspired by physics and by different scales. She's going to bring us on a bit of voyage beyond the zeros and ones, and she's going to do that together with Franco-Taiwanese artist Yifang Lin. Please welcome Wenqi and Yifang.
Future quantum. Dance. Body and movement. 0 and 1. Particle and wave. What is the link from dance to quantum? We live in a classical world, and for us, quantum is invisible. It surrounds us. It is microscopic, but also at the largest scales. Can the concepts of quantum, particle-wave duality, transition between two states with nothing in between them, be mapped to the body, to movement, to stillness? Moving towards the horizon is a dance piece, which celebrates the dance of light and water. I dance during the sunrise to welcome the light to arrive. Then I dance to the sunset to say farewell to the light and welcome the night, the darkness to fall. In this piece, I wanted to create a moment where people can contemplate how time flows. A story where you become sensitive to the nature around you and focus on the horizon. A universe where you dive into a different space and time, and the world slows down. My body is a metaphor to capture the dance of light and water. It is never still or unchanged. It is constantly moving, changing, flowing like water in the direction of somewhere. In performance, we said, time is ephemeral. As a dancer, I look at how I can think of quantum's constant movement as a dance dialogue at the human scale. But the natural scale for quantum is at the level of the atom, where light, particles, waves, movement are in constant exchange. The night canopy of stars originates in quantum phenomenon in atoms, in exchange between elementary particles. Light, in particular, spreads, oscillates, interferes. Wave infinite is a kinetic installation. The initial idea is to illustrate the invisible movement of life in wave form, like the wave signals from daily electronic. The invitation is for the audience to sit or lie under the installation, as if they are stargazing in the middle of the city. The Taiwanese author Wu Mingyi inspired me while I was creating this piece. He asked, "Why are people from any culture so obsessed with the stars? Since ancient times, human beings have learned to look up to the sky and connect incomprehensible natural phenomenon with personal and national destiny." Then he goes on to say that he thinks what people are fascinated by or think will affect their own destiny is not purely stars or constellations, but light. From the smallest scale to the largest, quantum is not only confined to tiny atoms, and the most intriguing aspects appear, where our classical worldview in the form of flat space-time and general relativity intersects with quantum phenomenon at the edge of black holes. a realm that can only be imagined via a language of dance that is no longer continuous but digitized, discontinuous, fragmented. Dancing Gravity is an experimental performance project on how to imagine and perceive gravity with the movement of dance, sound, and light. We invited a dancer, a sound designer, and VR artist to collaborate and create a piece for an online audience in the middle of the pandemic. In the scale of a human, today I presented you a journey that starts 8 years ago. When I first came to CERN, searching for the interconnectivity with everything, traveled back home with many questions of meaning, beliefs, and facts. I then produced my first piece with Yifan into the realm of art and science, called Unconditional Love and Fact. The performative presentation today is a reflection of my previous work, of my previous collaborations. It is an acknowledgement of how this quest into the realm of art and science shifted my artistic language, expanded the way and formats I work with, allowing me to engage with the different audiences. This presentation is also an experiment in itself. I wanted to see how different elements can coexist and interact with each other. A speaker, a dancer, text, music, videos, costume, and light into the stage. This is a collective work that we have created together. Me, Ivan, Michael, Sylvia, Claudia, Monica, Jill, Robert, Xenia, Zoe, and everyone behind the stage supporting us. And of course, each one of you here listening. You all have now also become part of this ephemeral performance. We are all like quantum particles. Will we forever be entangled? Thank you.
Thank you, Wenxi and Yifang. And this brings us almost to the end of the evening. I hope we are all going to go home having understood a little bit more about quantum. Before we end, I would like to thank a few people, actually. First of all, let's give a big entangled applause to all the speakers and performers. And then another big superposed applause to Claudio Marcelloni, the team at CERN, and everybody else who has helped make this happen.